Good evening, everyone. My name is Andrew Fracknoy. I'm the astronomy instructor here at Foothill College in Silicon Valley, and it's a great pleasure for me to welcome everyone at Smithwick Theater and everyone watching or listening on the web to the new 2012-2013 Silicon Valley Astronomy Lecture Series. 6 times every school year, we feature noted astronomers telling us about the exciting developments in our exploration of the universe. And there are few topics as exciting as the one our speaker is treating tonight. Just yesterday, the announcement came of the discovery of a planet orbiting the nearest star, one of the 2 stars in the Alpha Centauri system. And we're delighted that there's so much going on that we could have Dr. Battaglia, who's spoken with us before, back to catch us up on what's happening with planets elsewhere. Our speaker, Dr. Natalie Battaglia, is a research astronomer at NASA's Ames Research Center here in Mountain View, and she is the mission scientist for NASA's Kepler mission, which we're delighted is now in its extended mission phase. Dr. Battaglia holds a doctorate in astrophysics from the University of California at Santa Cruz. She started her career studying young stars like the sun, but she was so inspired by this field of discovering planets elsewhere that she came to NASA Ames, joining the team, working on the really amazing technology that is enabling us now to find planets like the Earth around stars far, far away. 12 years after she began, Dr. Battaglia stands poised with the Kepler team to make discoveries that until recently have only been in the realm of science fiction, but now are becoming our scientific reality. It's my great pleasure to reintroduce to you our speaker discussing finding the next Earth, the latest results from Kepler, Dr. Natalie Battaglia.
Good evening. Thank you for coming out on this beautiful autumn Wednesday evening. Students that are here for extra credit, I'm honored to be able to improve your grades, so thanks for coming. And thank you to the organizers, of course, to Andy and the sponsoring organizations for inviting me to come talk about this really fantastic subject that I'm really privileged, actually, to be able to come speak about. Finding the next Earth. NASA's on a quest. NASA's on a quest to find a planet like Earth. Moreover, NASA's on a quest to find life in the galaxy. And people don't realize that. Most people think NASA's about astronauts only. But no, we send robots out into the solar system, and we probe the galaxy for planets like Earth and ultimately for life. And I'm going to tell you about the Kepler mission, which is one baby step towards that objective of finding the next Earth and ultimately finding life in our galaxy. And so let me start with a figure that you're probably all very familiar with. Just a bunch of balls. In fact, you're going to see lots of pictures and cartoons of balls throughout this talk. So this is a bunch of little balls on a table to show you the relative sizes between planets and stars. This is our own solar system. Planets are a cosmic afterthought, right? Planets are nothing. They are the debris. If the sun were my mother, she would have swept all those planets away to clean up her house. Planets are this cosmic afterthought. And yet, they really are the most interesting thing in the universe, right? That's the cradle of life. But I show this picture in order to drive home the point that they are very tiny compared to their stars. In fact, the brightness, the reflected light from a planet, is about 10 billion times fainter than the brightness of a star. And so planets are literally lost in the glare of a star, right? It's like trying to find a firefly around the brightest man-made spotlight down in Los Angeles as viewed from New York, right? It's very difficult to do. So we don't actually take telescopes, or very rarely do we take telescopes and tool them around the sky, pointing, looking up in the sky for planets. We detect and discover these planets by indirect means, and in fact, we discover them by inferring their existence, taking observations of the stars themselves. There's something about the star, about the light that we collect from the star, that tells us of the existence of the planets. This is a cartoon from a well-known website, at least in science circles, called XKCD. Again, it's another cartoon of balls. These are all the known exoplanets orbiting other stars in our galaxy, and that number is quickly approaching 1,000. Right now, it's almost at 800, 786 as of the time of this cartoon. And what's interesting about this cartoon is that all of the balls that you see there of these confirmed exoplanets are to scale, relative size. And in the middle of this diagram, there's a tiny little box. You can barely see it. It's right in the middle. It has a gray background, kind of underneath the word to scale, is a box of our own solar system planets. And the primary planets there are Jupiter and Saturn that you can see, right? So if you just scan this diagram, what you notice right away is that most of these confirmed planets are larger than Jupiter and Saturn. That doesn't mean that most of the planets in the galaxy are larger than Jupiter and Saturn. It means that those are the easiest ones to find. And so our ground-based telescopes that are finding most of these planets so far have this bias towards finding those that are the easiest to discover. And those are the largest planets at the shortest orbital periods. Okay? Now, there are lots of small dots there, too. So if you don't believe me about the actual statistics, that more than 50% of them here are larger than Jupiter, then I offer you the periodic table. Not the periodic table of chemistry, of the elements, but the periodic table of exoplanets. And so the way that this is arranged is by size. On the left-hand side, we have Mercury-sized, sub-Terrans, so slightly smaller than Earth, Earth-sized or Terrans, super-Terrans, Neptunians, and Jovians going over to the right. And from top to bottom, we have some measure of how much energy is being received by that planet due to its parent star that it orbits. That would translate to a temperature of sorts. We'll think of it as a temperature. So going from the hot zone, which would be very close up to its parent star, to the warm, what we call habitable zone, and I'll come back to that point in a second, and then the cold zone, which would be further out. And so what you see in this diagram, indeed, the numbers of planets in each of these categories is way shifted to the right. It's weighted down over there on the right with the Jovian-sized planets in the hot zone. Those are most of the confirmed planets. So that's kind of the general picture. Now, what I'd like to also mention is how these exoplanets, the majority of them, have been discovered and confirmed. This is a little cartoon of a star and a planet in their orbital dance. We know that planets orbit their stars due to gravity. But what's not so obvious is that stars also orbit their planets. In fact, the two systems, the two objects, as they are gravitationally bound and orbiting about each other, are orbiting about their common center of mass. So if you imagine a bar connecting them and you wanted to put your finger at that balance point, you know it would be very close to the star itself because that's the heaviest object. That's the point about which these things are orbiting. So the planet is accelerating a lot in its orbit. We barely perceive the motion of our own central sun, for example, but it does indeed wobble as it orbits about that common center of mass. And so the Doppler technique, which you hear a lot about in the media, is this method that detects that wobble. It's often called the wobble method. What we do is we take a spectrum of a star, and this is an example of a spectrum. Red at the top all the way down to violet at the bottom. It's chopped up and stacked. So you see this beautiful rainbow, and what you notice right away is that there are certain colors missing, these little segments that are perfectly black. where energy or light is not reaching our telescope. Those are called absorption lines. And if the source of the light, which in this case is the star, if it is wobbling back and forth, the color, the exact color of those missing photons is going to shift back and forth towards the blue and towards the red end of the spectrum. And that's called the Doppler effect. It's exactly analogous to the change in pitch that you hear when an ambulance approaches you with its siren on and then goes away from you. You hear that shift in pitch. And so this is it is analogous, except that that shift is very, very tiny. Let's zoom in here on one of these absorption lines and superimpose it against a grid of pixels that we use to measure light. You can see as that absorption line shifts back and forth, different pixels will measure different amounts of light. So that's what we're trying to measure when we do this Doppler technique. And the typical speeds of an exoplanet are walking speeds, right? You're trying to detect a Doppler shift of light for an object that's moving at like a walking speed, some meters per second, okay? It's very small. So it requires really our most powerful telescopes to do this, our most sensitive instruments. The Kepler team uses the twin telescopes at the Keck Observatory, the Keck 10-meter telescopes, opening their eyes to the universe and taking these very important measurements. And the Keck Observatory is responsible for many of the planet discoveries. But the Doppler technique, with the best technology that we have, is yielding a precision of about a meter per second, right? But these really interesting planets, these Earth analog planets that we're trying to detect, like Earth, let's say a planet exactly like the Earth out at a 365-day orbit, that's going to induce a Doppler shift of maybe an ant crawling speed, some tens of centimeters per second. We don't have the technology to do that. So how are we going to find these Earth-sized planets, especially those that are potentially habitable? And that's where Kepler enters. Kepler is a NASA mission. It's a space-based telescope whose objective is to answer this one very, very simple question. What fraction of stars in our galaxy harbor potentially habitable Earth-sized planets? Okay? And there's a cartoon here of the spacecraft itself. Well, what do I mean by habitable, potentially habitable? We're going to take a very simplistic definition of what habitability means, and that's that the planet is orbiting at a distance which is neither too hot nor too cold for the existence of liquid water on the surface. That area, that region around the star is called the habitable zone, where the temperatures are just right, this Goldilocks zone that I'm sure many of you have heard about in the media. So here's a cartoon that shows that the Goldilocks zone, which is colored green, shaded green in each of these diagrams, it's different. It depends on what kind of a campfire you have in the middle, namely the star. If it's a really hot star, the habitable zone is going to be further away. If it's a really cool star, you got to cozy up next to it, right? So how are we going to know if a planet is in this habitable zone? Using Kepler's laws of planetary motion. Hence the name of the project. We measure the orbital period, how long it takes the planet to go around once, and that's directly related to how far away the planet is from the star. If we know how far away it is, and we know how bright the campfire is, we know what the temperatures would be near that surface, or how much energy it would be receiving. Okay? So how do we go about doing this? That's all well and fine, but how are we going to detect them if not by the Doppler technique? And so I show you this picture. I hope that this is familiar to you. This is an International Space Station picture of the surface of the Earth, and that big black dot that you see, it's not a hurricane. It's actually the shadow of our moon projected onto the surface of the planet. Every rocky object orbiting a star is casting a shadow out into space, right? We've seen it. We experience it. People that are standing inside that black spot are going to see a total or a solar eclipse, right? The sun is going to get blocked out. Now, what about the Earth? The Earth also is casting a shadow out into space, right? We're not so conscious of it until we have a lunar eclipse, where we literally see our own shadow projected onto the surface of the moon, right? You stare at the limb of that shadow. There's somebody standing right on that limb, somebody on Earth, right? You're looking at another part of the Earth. That's our shadow. And so perhaps this point was driven home to you on June 5th. How many of you saw an astronomical event on June 5th? Maybe a quarter of you. Maybe this will jog your memory. This is the Hinode spacecraft video of the transit of the planet Venus across the surface of the sun. So watching this planet trek its way across the surface of the sun, you can really begin to imagine that that little tiny rock is indeed casting its shadow out into space. You also realize how tiny that shadow is going to be, right? It's such a small amount of dimming of light. And yet that's exactly how we're going to infer the existence of planets. That's what Kepler is going to do. We're going to measure the brightnesses of stars very, very precisely. We are going to measure those brightnesses as a function of time, as shown in the bottom plot, the green trace, and wait for a momentary dimming of light that will occur if a planet in its orbit about the star happens to be aligned in your line of sight, so that that shadow sweeps across the face of the telescope and is perceived through our instruments as a dimming of light, okay? So that event is called a transit. It transits across the front. And this green trace that I have here, we tend to call them light curves. They're just simply brightness measurements as a function of time, and we call those light curves. For a planet like Jupiter, that dimming of light is about 1%. And that's really easy. We can do that from the ground. We don't need to build a $500 million spacecraft to find a Jupiter transiting a star. It's a 1% change in brightness. But an Earth-like planet looks like that. You can barely see it. It's a 1 part per 10,000 change in brightness. The analogy I like to give is to imagine the very tallest hotel in downtown San Francisco. Maybe it's 30, 40 stories high, and every single room in that hotel is occupied. And it's nighttime. And every single occupant has the light of their room on. And one person in that hotel lowers their blinds by about 2 centimeters. That's the change in brightness that we have to be able to measure. We need part per million precision in order to do that. And so while the science, the idea behind this is very simple, very elegant, very simple, we can all understand this quite easily, what makes it a technological feat is achieving that precision, this part per million precision. And we do that by building a very stable camera and by engineering it inside of a very stable spacecraft. We know exactly what that spacecraft is going to do when it's in space. We know exactly how it's going to jitter. We know exactly how temperature is going to affect it. And it's all been designed and engineered ingeniously so that those things create a very stable instrument. What you're seeing here is a mosaic of CCD detectors. These are light measuring devices. It's the same exact thing that you have in your cell phone or your digital camera when you take a picture, right? Except the one in your camera is about the size of your thumbnail. All right, this is 1 square foot of silicon, 42 different detectors mosaicked together. And that is what the light is going to fall on from our telescope, and that's what's going to count the brightness of all the stars. So we need very good sensitivity in order to find these planets, but we also need to observe a lot of stars. What's the probability that a planet is going to be orbiting exactly on its side so that that shadow does sweep across your telescope? It's very small. For a Earth-Sun analog, that probability is 0.5%. So that means you have to observe 200 of these things to find just one, right? So you want to observe a lot of stars, and where we have a lot of stars is in the plane of the Milky Way galaxy. So Kepler is staring up at this patch of the sky. There's that pattern of CCD detectors that I showed you projected onto the sky. It's about an open hand against the sky, 100 square degrees. That doesn't seem like a lot, but the full moon would fit quite neatly in one of those gaps between the detectors. All right, so it's a very large field of view on the sky. There are about 4.5 million stars in our galaxy alone in this little patch of sky. We've cherry-picked about 150,000 that we've been observing regularly since the mission launched. And since this is a space-based mission, I have to show you a picture of a rocket, the obligatory picture of the launch. The spacecraft launched in March of 2009, so we've been up there taking these observations for about 3.5 years now. We take a brightness measurement of all 150,000 stars simultaneously every 30 minutes, and we've been doing that since we launched the spacecraft. So billions and billions of measurements are going into the detection of these planets. All right. So I'd like to first give you the bird's eye view of what we've discovered so far in these 3 years. We've analyzed now about 1.5 years worth of data, okay? So I'm going to show you the results of that analysis. And I'm going to do this by showing you a scatter plot. On the y-axis, we have the size of the planet, the radius, against the orbital period on the x-axis. Now, the size of the planet we get simply by measuring how much of a dimming of light occurs. That depends on the size of the occulting object. And the orbital period we get by measuring, by clocking the interval between dimmings of light, right? And so the white points that you see on this diagram, delineated by these horizontal lines marking Jupiter, Neptune, and Earth sizes, these were the transiting planets, exoplanets, that were known before Kepler launched, okay? And so you see that they cluster, there's a swarm of them there around Jupiter size, and orbital periods of about 3 days, if you can read the x-axis. 3 days, right? Mercury in our solar system is 89. So 3 days is very, very close to its parent star and mostly Jupiter-sized. So I'm going to show you now a succession of 3 plots that adds the planet candidates that Kepler has found in its data. 3 of them because we've published so far 3 catalogs, one in 2010, one in 2011, one in 2012, all right? One of these catalogs I've already shown in a lecture here in this auditorium. So those of you who were here have seen this already. And this is what that plot looked like the last time I was here, all right? So let's go back and forth between these 2. Already in 2010, we had 312 planet candidates, and you can see that the statistics changed completely. No longer were the transiting planets up at Jupiter sizes in orbital periods of 3 days. Now, something like 90% of these are smaller than Neptune, right? Completely different than what the ground-based surveys looked like. So that was the scenario in 2010. Now let me just fast forward. Let's get ourselves up to date. Here's 2011 and 2012. We now have over 2,300 planet candidates in the data that we've seen. Right? Thank you, that was nice. All right. Going from blue to red to yellow, you notice that the parameter space is broadening, right? They're spilling out. They're spilling out to smaller sizes and longer orbital periods, which is exactly what you would expect just by way of collecting more data, analyzing more data, right? The other thing that you notice is that the bottom right-hand corner of this plot is relatively empty, and that's exactly where Earth resides. And that's also to be expected because Earth has an orbital period of 1 year. In order to measure the orbital period of a planet through its dimmings, its periodic dimmings of light, we need 3 years to be able to see it. And this analysis is based on about 1.5 years worth of data. So we're working our way down towards the bottom right-hand corner of this plot. You'll have to invite me back, Andy, again in another year to give you the update. All right, so this is what it looks like. I want to say a little bit more about it, but I think I'll do it through this very nice animation by the same fellow who did the animation that was playing before, and I'll give him credit here in a second. It's a pity to have to talk through it because the music is so beautiful. But this gives you a feel for the sheer volume of planets that we're talking about. At any moment in time, there are hundreds of Kepler planets that are in the process of transiting their parent stars. You can see that quite clearly in this diagram, right? There are two different size scales that are being shown here. The planets themselves are scaled relative to one another and their parent stars. So they're all tied to, the planets are all orbiting different kinds of stars with different distances, but their sizes are set so that they're all relative to this one star in the middle. We're going to see an edge-on view, and then we'll see a face-on view of this collection. Of course, all the planets don't orbit the same star, but we just wanted to, for display purposes, to show them collectively. There are colors that you're going to see. The colors indicate something about the temperature, red being hot and then working its way out towards cooler temperatures. But these lines that you see here, these three circles, delineate orbits in our own solar system, namely that of Mercury, Venus, and Earth. And so this animation clearly shows that the large majority of the planets in our samples so far are at short orbital periods, interior to the 89 days of Mercury in our own solar system. There are two reasons for that. One, as I said, is because we've only analyzed about a year and a half worth of data. But also the second reason is that the probability of having a transit event decreases as you go out in orbital period. Because the farther away the planet is, the smaller the angle is required to sweep it clear out of the line of sight so that it is no longer transiting. So we expect to find fewer planets at longer orbital periods. Those will peter out, but the mission has been designed so that we will find significant numbers even at orbital periods of 3 years. And now that Kepler has an extended mission for another 4 years, we hope to be able to go out even to 2-year orbital periods. In this sample of 2,300 planet candidates, 250 are 1.25 times the radius of the Earth or smaller. 250 what we call Earth-sized planet candidates. 50 of these candidates are in the purported habitable zone. The majority of those, however, are Jupiter and Neptune sized. As you saw before, the bottom right-hand corner of that diagram wasn't yet well populated, right? So far, we've got 50 planet candidates in the habitable zone, but most of them are super-Earth, Neptune, and Jupiter sized. The fellow who did these animations is Alex Parker. He's at CFA in Boston. He's done some really beautiful work. I encourage you to look at all of the work that he's done on Vimeo. Okay, so let's go back to this exoplanet periodic table. I think you already have a good feel for how the statistics have changed, right? Between the exoplanets that were largely discovered from the Doppler surveys, that 780 some odd planet candidates, compared with this 2,300, right? But let's just remind ourselves that in the exoplanet periodic table of the 700 and some odd planet candidates, they were weighted over towards the right. The largest bin was up there at the hot Jupiters in the upper right-hand corner. Let's see how that's changed. Here's the periodic table of Kepler candidates. So where is the square that is the most populated now? Right here. Super-Earths. 1,216 of the planet candidates are between 1.25 and twice the size of the Earth, or thereabouts. Actually, and I'm sorry, their metric goes from 1.25 to 2.5. Interestingly, in our own solar system, we go from the Earth at one Earth radius The next biggest planet is Neptune at about 4 Earth radii. In our own solar system, we have nothing in between. And yet, that's what we're finding the most of. So it's going to be very, very interesting to learn about these kinds of planets, examples of which we have none, right? All right. We could go back to that scatter plot. Here's the same thing, radius of the planet on the y-axis, but instead of orbital period on the x-axis, I've changed it to temperature, that temperature that's related to how far away you're standing from a star of a certain brightness and temperature, right? And this green band here is the purported habitable zone. And all of these candidates that fall within that green band are in the habitable zone. And here is lonely Earth. Not a lot of planet candidates down here, but you notice there is one, just kind of kissing that little region of the parameter space. And I'll show you its data in a second. This is a composite of the best planet candidates in the habitable zone so far to date. This was constructed by our friends at the Virtual Planetary Habitability Laboratory in Puerto Rico. And so we've got our solar system planets in the upper right for comparison. We've got 4 of the 786 confirmed planets in the upper left. And then down here in the bottom, we have the Kepler planet candidates drawn from this sample of 2,300. And there are 20 some odd, now I don't remember the exact, 27 Kepler candidates. And you might be wondering why I keep calling these candidates. And in fact, in this slide, if you can read the tiny print, it says 4 confirmed and 27 unconfirmed Kepler candidates. And the reason for that is because there are astrophysical signals in nature that can mimic a dimming of light due to a planet. And it's estimated that the fraction of planets, of transit events in our data sample that are these other astrophysical signals is going to be something like 15% probably on average, maybe 10 or even 5% up to maybe as high as 20. But even if it's as high as 20 out of 2,300 planet candidates, you're still looking, 80% of them are going to be real. So the same applies here, about 80% of them, and that's a conservative estimate, 80% of these guys are going to be real. All right, and just for kicks, I wanted to show you some actual data. This is the dimming of light due to that one object right around the Earth. It is a habitable zone, Earth-sized planet candidate. KOI 2124, we call it, is orbiting a star that's 4,000 degrees with an orbital period of 42 days and has a radius of 1.02 Earth radii. It could be some other astrophysical signal. This one is not confirmed yet, but it has about an 80% chance of being real. The other thing I wanted to mention is illustrated in this slide. Now what we've done is we've taken horizontal groupings of planet candidates, shown, scaled, relative sizes are correct, but every horizontal line is a family of planets orbiting the same stars. 900 of the 2,300 planet candidates that I showed you are associated with a single star. So not only can we learn about single worlds, we can also learn about the architectures of systems. We can learn about solar systems because we have so many of these multiple planet systems. And here I'm showing they're stacked in order of the orbital period of the innermost planet going up. And this collection of what we call multis only represents about 1/3 of the multiple systems that we've seen so far. All right. I want to shift a little bit now and talk about some of the planets that have had their status upgraded from candidate to confirmed planet. So these are all worlds that we know something about. We've characterized them. We've done follow-up observations that have allowed us to learn something about them so that they become tangible, they become real, more like destinations and not just something in our head or something in a catalog. And I'm going to start right off the bat. Well, let me show this, another collection of round balls. This does not represent all of them. As of today, we have, depends on exactly how you count it, 78 officially confirmed planets, and there are another 25 or so that are in the literature undergoing the review process. So about over 100 confirmed systems, and here are some of them. And I just wanted to point out that red box there on the right is Jupiter. The majority of the systems that are confirmed are smaller than Jupiter. In fact, the majority are smaller than Neptune. So Kepler is really focusing its resources on confirming and characterizing the smallest planets, because that's really what we're being paid to do. That is our focus. And here's Earth. We have many down here that are Earth-sized, so I'd like to show you a few of those. These are Kepler's first truly Earth-sized planets. This is the Kepler 20 system. The star itself is Kepler 20. Planets are given lowercase letters, so this is 20E and F, which implies that there is also a B, C, and D, which there is. And they don't go in order of the letters. I think it goes, let's see, it goes B, E, C, F, D, I think is the order. Kepler 20E and 20F are both about Earth size. One is slightly smaller, one is slightly larger. And these planets were confirmed by doing follow-up observations with ground-based telescopes to eliminate every single one of those false positive scenarios, those astrophysical signals that can mimic a planet transit. We've ruled them out systematically by doing follow-up observations. So this was a very important milestone for our team, the confirmation of the first Earth-sized planets. They orbit at periods of 6 days, the inner one, and about 20 days, the outer one. So they're still very hot. In fact, the artist's concept of Kepler 20e, this is not a real picture. It's our imagination, a little flight of fancy to imagine what this planet might be like. It's illustrated as a very scorched world because at an orbital period of just 6 days, the temperatures there are going to be too hot to sustain life as we know it. But following on its heels was the confirmation of Kepler's first planet in the habitable zone. And the name of this star is Kepler 22. And here is the artist's concept of the planet itself, which is Kepler 22b, orbiting a star very much like our own sun, a G-type star, at an orbital period of about 290 days. It's 2.38 times the radius of the Earth. And again, we have no examples of planets like this in our own solar system. We don't know what it's going to be like. We have confirmed the existence of the planet in the same way that we confirmed the existence of the Kepler 20 Earth-sized planets, by eliminating all of these other things that it could potentially be. But we don't actually have a mass. So we don't know what the density is. You can get the density if you've got mass and you've got volume. Density is mass divided by volume, right? But for the volume, you need to know the radius, and Kepler tells us that. But in order to get the density, you would also need the mass. Density is important. It's a very interesting quantity because it tells you something about what the planet is made out of, right? Our own Earth has a density of about 5.5 grams per cubic centimeter, but Jupiter has a density of about 1. So our own solar system planets have very different densities depending on what they're made out of, right? And so if we can get the mass, we can get the density, and we can say something about the composition. For this planet, even though it is in the habitable zone, we really don't know what its density is going to be. This could be, I suppose, something rocky, although our theoreticians are telling us that that's not likely. For that reason, we do not call this a super Earth, even though it has a radius of only 2.4 times the Earth's radius. We call this a mini Neptune because we suspect that planets this size have a high content of hydrogen and helium, which could imply, because this thing is in the habitable zone, it could be enshrouded by a liquid ocean. We don't know. It might also be icy. We don't exactly know how planets, if you take a planet like Neptune, make it a little bit smaller, and you plunk it down at 1 astronomical unit, the Earth's orbit, what happens to it? We don't know. Theoreticians are working on this problem right now, trying to figure it out. But it depends. It depends on how far the radiation reaches down into that planet, how much it's going to outgas, if it's going to create a thick, hazy, steamy atmosphere. All of those things are variables, and it's very speculative right now. So the artist has drawn this as a water world. You can imagine the Loch Ness Monster swimming there if you like. That's okay. But the situation is different for Kepler 10. I've written here that this is Kepler's first rocky planet. And by way of saying that, you're probably already guessing that we do know something about the mass of Kepler 10. So let me tell you a little bit about Kepler 10. Here is the data. And this is the Kepler data on the left. Every white point that you see is a brightness measurement. And it was taken, this data was taken over a period of, I think, 22 months. And every dimming of light from every orbit was chopped up and stacked on top of each other, like one of those paper doll chains that you can make. So they're folded together, and that's why you see lots and lots of white points overlapping each other. So this is the dimming of light. It's this 1 part per 10,000, like I spoke of before, which speaks to a radius of just 40% larger than the Earth, 1.4 times the Earth's radius. What are planets at 1.4 Earth radius like? We don't know. You know, it could be like a comet. You know, this big giant snowball hurtling through the stellar system. Maybe, can you make a big giant comet that's 1.4 Earth radius coming from the outer solar system? Sure, you could. Could you get it to orbit at this orbital period? I don't know. So what we really want to do is we want to find out its mass. And so we started observing this candidate at the Keck 10-meter telescope pretty much immediately when we first detected the signal. And here on the right is the result of those observations. And so I have the velocity as a function of orbital phase, and you see the points undulating up and then down, red shifted and blue shifted as the star itself wobbles to and fro due to that tiny little tug from an almost Earth-sized planet. And so the amount of wobble that the star undergoes tells you the strength of that tug, which tells you the mass of the planet. And in this case, it's only 4.5 times the mass of the Earth. And you put those two things together, and it gives a density of about 9 grams per cubic centimeter. And as I said, our Earth is like 5.5, right? There is no theoretical model consistent with this data within the error bars except for one of a rocky planet. And that's how we know that Kepler 10b is indeed a rocky world. You could not make a planet like this if it were mostly hydrogen and helium at that density. All right, let's see. I think I'm going to skip forward. And the other planet I'd like to tell you about is actually a multi-planet system that has not 1, 2, 3, 4, or 5 transiting planets, but 6. This is the Kepler 11 system. 6 transiting planets. Here is a face-on version. And 5 of those planets, these 5 interior planets, are all orbiting interior to what would be Mercury in our own solar system. And one is out kind of between Mercury and Venus. So this is very different than something that we have in our own solar system. Most of these planets are about twice the size of the Earth. But what's interesting to think about, you know, we've already talked about how planets can tug on their star. But if you pack planets tightly together, they can also tug on each other. And that's exactly what this system is. It's a dynamically packed system. 5 planets orbiting interior to what would be Mercury in our own solar system, right? And so under those conditions, planets do start to tug on each other, and you get a scenario like this. If you watch these orbits carefully, you'll notice a couple of things. One, you notice that the velocities are not perfectly smooth. It goes in fits and starts. The planets kind of jerkily speed up, slow down. You also notice that the loops, these white traces, don't perfectly close on themselves. The orbits each time are slightly different. And that's a consequence of the planets exchanging gravitational energy because they are so closely packed. Not as illustrated in this diagram, of course. This is very much exaggerated, but you get the idea. And so this manifests itself in the data as a perturbation, a difference in the arrival time of the dimmings of light. When you think it should occur, it's not there. It arrived maybe a little bit too early or a little bit too late. And that's because of these orbital velocities going in fits and starts. And by measuring how much too early or how much too late, we can get an idea of the strength of that tug of one planet due to the other. And by doing a complete dynamical solution, we can then determine the masses of the planets without needing to go to the Keck 10-meter telescope at all, right? So this has been tremendously powerful. It has exceeded our expectations. The majority of Kepler planets that have been confirmed so far have been done with this technique. It's called transit timing variations. So we have great hope that this method will yield the mass of a planet the size of the Earth near or in the habitable zone. We have great hope that that will happen. The other interesting thing that Kepler has done is proven that George Lucas was right. Perhaps you've heard this already. He was very psychic in this regard. This is not a Kepler planet system. This is Luke Skywalker on his home planet Tatooine. But Kepler did detect the first circumbinary planet, which means that planets can form and exist stably in orbit about not one but two stars, meaning that on the surface of that planet you would enjoy not one sunset every night but two. And moreover, the stars orbit each other and you would see them switch place and eclipse one another. So it'd be quite a spectacular evening sky, I think. There have been several of these that have come out recently. This is Kepler 47, which shows not one but two planets in a circumbinary configuration. Here are the two stars orbiting each other, and then you have two Neptune-sized planets. And then just earlier this week, at the DPS meeting in Reno, we had the announcement that actually we're very excited about of a Saturn-sized planet, again orbiting two stars, in a system that has two other stars gravitationally bound to it. This is a 4-star system. 2 stars over here orbiting one another, 2 stars over here orbiting one another. Both of those systems are orbiting one another, and a planet orbiting one of those binary systems. Who knew nature would be so diverse, right? I mean, who knew that you could do this, that could exist in a stable configuration over many years? But indeed it can. And here's the thing. When you look up in the sky at night, 1/2 of those points of light that you see are actually binary stars, multiple star systems. The fact that planets can exist around these stars is telling us that nature is even more prolific than we imagined from our 2,300 planet candidates, right? All right. And the reason that this is so special is that the signal of this planet in this system was discovered not by a scientist, but by a citizen who, out of the love of his love of stars and his passion for science, was combing through Kepler data on a website called planethunters.org, where citizens can actually interact with Kepler data, examine it, and find their own planets. And this is actually becoming quite successful. So this was discovered in that way. And if you'd like to check it out, here's the frontispiece of their website. And the website is planethunters.org. I encourage you to check it out. All right. So here we are back at this footprint on the sky, this mosaic of CCD detectors on the sky, and it's filled with these colorful skittles that look like Skittles, looks like candy, marking the positions of Kepler's planet candidates. And so now we want to ask ourselves the question, okay, fine, so you've found 2,300 planet candidates, and you observed 150,000 stars. So I can do the math, right? 2,300 divided by 150,000, is that about the fraction of stars that has planets? Well, no, not at all. Why not? Because the probability of being in a configuration so that that shadow sweeps across your telescope is 0.5%, 10% at the very best. So for every one that we detected in that geometrical configuration, there's another 50, 100, 200 out there that were not aligned just right, all right? Now imagine, this is only 1/400th of the entire sky. And this is probing out to a distance of only 3,000 light years. Our galaxy is 100,000 light years across. And you tell me, how can there not be life in the galaxy, right? It's looking like nature makes small planets efficiently. And it's looking from this data alone that there are, on average, about 0.35 planets per star. Of course, you can't have a fraction of a planet around a star, but if you average it over the whole sample. And that number is growing. That number is only for planets out to orbital periods of about 50 days. As we collect more and more data, that number is going to grow. So you'll see that play out in the next year or two. So now I would like to think a little bit about the future. This is a picture also taken by the International Space Station of the limb of the Earth. And the sun is just, I think, setting. Either setting or rising, I don't remember. I think it's sunset. So that means the space shuttle is going away. And the reason I like to show it is because of that thin blue haze that blankets our planet. That is our fragile atmosphere. And the sunlight in this geometrical configuration is filtering through that blue haze. And in doing so, the atmosphere of that planet, that blue haze, is leaving a little fingerprint on the light that we would catch in our telescope. And if we understand that fingerprint, we can learn what that atmosphere is composed of, right? And this is one of the other great advantages of discovering a transiting planet. Not just that you can get the radius and maybe the density, but also that you have this very special geometric configuration where the starlight is filtering through the atmosphere of that planet on its way to your telescope. So in the future, what we'd like to see happen is to build instruments that are capable of detecting that fingerprint of that atmosphere. Let's go back to the transit of Venus. Here it is again. And you can also see the haze enshrouding the planet Venus. But look how tiny it is. It's 1/200th the scale height of the atmosphere. If you add up all of that area, it's only 1/200th of the total area of that disk. And that disk itself is 1/10,000th of the area of the star. 1/200th of 1/10,000th. That's the signal that you're trying to get, right? So it's going to be very, very difficult to do this, but theoretically possible. If we can build sensitive enough instruments, we can do this, we can collect the light, we can see the signature of the atmosphere, and check to see what it's made out of. Let's just for dramatic effect, zoom out. Okay, just to give you a feeling for the 1/200th of the 1/10,000th. See how tiny that little black disk is there through the clouds. And what we would be looking for is something like this. This is a microscopic picture of cyanobacteria, pond scum. You didn't know pond scum was so exciting, but it is. Early in the Earth's history, life was pond scum. And that pond scum is responsible for giving early Earth, its atmosphere of oxygen that you and I breathe in this nice asbestos-free auditorium. And this microscopic picture of cyanobacteria has been caught in the act of metabolizing and creating that little bubble of oxygen that you and I depend on for life. It's evidence of life that populates the atmosphere. If we were to do this observation, check to see what an atmosphere is made out of, an atmosphere that's enshrouding an Earth-sized planet in the habitable zone, and we see a signature of oxygen, that is going to be a telltale signature of a living world. Not necessarily intelligent life, but a living world, right? Okay, and so finally, I cannot help but mention a little star called Alpha Centauri b. How many of you heard the news about this today? Please raise your hands. That's great, more than half of you. This is one of the brightest stars in the sky. Unfortunately, we can't see it because it's in the southern hemisphere. It's at a declination of minus 60 degrees. In fact, if you were at a latitude below minus 29 degrees or 29 degrees south, it would actually be a circumpolar star, kind of like the Big Dipper, or some of the stars in the Big Dipper. Here's the star, here's the constellation Centaurus. Here is Alpha Centauri, the brightest star of the constellation Centaurus. Alpha and Beta actually point to the Southern Cross, nearby which is the southern celestial pole. Alpha Centauri, as I said, is one of the brightest stars in the sky, but it's also the nearest star system at just a little bit over 4.3 light years away. It's a stone's throw. It's a cosmic stone's throw away. It's not just one star, it's actually three. Here is Alpha Centauri A and B. A is actually the brightest star in the system. B is the next brightest. A is a G-type star, kind of like our sun. B is a K-type star. It's cooler. But the way the artist depicted this, he has gotten close up to star B, and that's why it appears brighter in this image. And that's because the observations that have been done were collecting light from Alpha Centauri B. The star itself is smaller. Therefore, if a planet is tugging on it, it will move more. So the Doppler signal will be slightly larger than would be expected from a G-type star, right? And so astronomers have been doing this, have been observing this and taking spectra and looking for this signature of the Doppler effect around the star for quite some time. The European team has been doing this now for 4 years with 1 meter per second precision. In the 4 years they've been doing this, they have collected 459 velocity groups. Actually, they've actually collected even more, but they've averaged them together. They've taken them at very high cadence, averaged some of them together, producing 459 points over a 4-year period. A tremendous amount of data, requiring tremendous persistence. Now, in that data, there's basically been nothing. No giant planets. Giant planets would have stuck out like a sore thumb. There's been nothing. That was actually a good sign, because the Kepler data is showing us that if there is a giant planet in a short period orbit, chances are there are no Earth-sized planets. They probably get scattered out of the system. So that was actually a good sign. So they kept observing, and then what they found was that the velocity was kind of jumping up. It was all over the place. And that's because the velocity of the star itself is being influenced by intrinsic variations of the star that have nothing to do with the planet. The variations of the velocity, just due to the light output of the star, are larger than the signal that we're trying to see. And so they spent years trying to tease apart all of these different contributions. Star spots on the surface create a velocity variation. Granulation, convection on the star surface creates variations. Activity cycles, like our own solar cycle, right, the 11-year cycle, that also creates velocity variations. And so meticulously, they have filtered out all of these different components. And what they were left with and announced today, actually yesterday, but that's a longer story, is this. This is their velocity curve as a function of orbital phase. Every black point is one of these 459 observations. You can see if you just look at the black points, they're all over the place. You don't see any nice undulation going up and down. But if you take tiny sections and you average the velocities together, what emerges are these solid black points and their associated error bars. When you average a lot of measurements together, you beat down the noise and you tease out that signal. And this particular signal is only a half of a meter per second. 50 centimeters per second is the amplitude of that velocity variation. Kepler 10b, the 1.4 Earth radius planet that I showed you, was 3 meters per second. This is a half. Kepler 10b, I didn't mention, orbits its star with an orbital period of 0.89 days. It orbits its star once every 0.89 days. This particular guy, Alpha Centauri, capital B, little b for the planet, orbits its star once every 3.2 days or thereabouts. So it's still much, much too hot for life as we know it. Carbon molecules would break down at these temperatures, so we don't expect there to be life. So why is it important? To me, it's important. When I first saw this result, the first thing I thought was, wow, hello, neighbor. You know, let me go say hello. It's a stone's throw away. We know of planets like this, right? You saw Kepler 20e and F, same size, right? Even longer orbital period, so even closer to being potentially, towards the habitable zone. But this thing is 4.3 light years away. It's our neighbor. And I think that is something that's very profound. Everybody is very excited about this result because all of a sudden you are inspiring young people to have this destination within reach, right? You're inspiring them, giving them this destination. You can point to a star that has a planet that is Earth-sized, and as we know from Kepler, if it has one, it's likely to have more, which makes this a very, very compelling destination. We already are funding research to be able to send something like a cell phone with a little digital camera out into the galaxy at about 1/10 of the speed of light. Scientists think, engineers think that that's not completely unrealistic. We can probably accomplish that maybe within the next 50 or 100 years. So if you can accelerate a cell phone to about 1/10 the speed of light, you can get to Alpha Centauri within, 70 years or so, right? I mean, that's a new horizon for my grandchildren, right? And there's something fundamentally important about having new horizons. We are explorers. I don't know why, but we are. And we've always had new horizons. Some of you sitting in this audience had the moon as your new horizon. I myself had Mars as a new horizon. I felt that deeply when Pathfinder landed on the surface of Mars, for example. Now then the MER rovers and now Curiosity. So current generations have Mars as their new horizons. What's the new horizon for the future? Well, looking at this planet, I know that in 100 years we could have another planetary system as that new horizon. And there are children in this audience who are going to be capable of helping us get there. Besides the issue of survival, the fact that we do have to get off this planet one day for our own survival, I think that it's fundamentally important that we get off this planet as a matter of the evolution of our own species. I think exploration and having those new horizons is fundamentally important for us as a species in our cultural and perhaps intellectual evolution. So I would argue that this is exactly what we should be doing, that this is going to invigorate NASA science, space exploration, commercial enterprises, and this is a damn exciting time. So I hope you're enjoying it. Sorry, kids. I'll stop talking now and allow you guys to ask some questions. And do feel free to leave if you need to get out, I understand.
Okay, so in fact, let's remind everyone that if you have questions for Dr. Bataya, we do have 2 microphones set up in the middle of the auditorium, just in front of that, where that railing is. We encourage you to please keep your questions short, and I'm going to ask you to pick one and then the other in a fair order. And if people would line up at the microphones, we'll have a period of questions.
So yes, please go ahead and start.
So your data showed a lot of planets very close to the stars with very short periods. Is that exactly what you expected in terms of when you look at our own solar system? Because we don't have anything close to that. We have all those longer ones. But I understand your data is skewed because of the way you're looking and all you explained. Mm-hmm. So is our solar system just very weird? Or is it exactly normal in the distribution? We just don't see it in what you're collecting so far.
It's an excellent question, and we should be able to say something about that when the day is done, because we do have data that speaks to the architectures of systems. It's looking like our solar system might be an oddball. As you mentioned, we don't have any of those planets. We don't have any super-Earths between the size of the Earth and Neptune. However, we have this observational bias, so we have to take that out of the equation. It's too early to tell. I'm not going to go out on the limb and say that our solar system is unusual, because it's too early to tell, but I do appreciate the question. Okay. Yes?
Yeah, how much more powerful do your sensors need to be to infer if some of these planets have their own satellites?
I'm sorry, repeat the question. How much more powerful?
Do your sensors need to be to infer that these planets that you're finding have a system of their own satellites, kind of like the Jovian system?
Yeah, exactly. Great question. There is a team of scientists who are examining the data of all of the planets in the habitable zone, Jupiter-sized planets in the habitable zone. Why? Because we've all seen the movie Avatar, right? There's a Pandora out there, right? Honestly, a Jupiter-sized planet could have a kind of lunar or Mercurian or even Earth-sized satellite. And if it's in the habitable zone, that makes that object extremely interesting. In theory, it's possible around some of our systems to detect such a signal if indeed that object is approaching Mercury, Mars, Earth sizes. Whether or not that bears fruit, I don't know. But it is in theory possible for a small number of our stars, of our brighter stars. Let's see, yes?
This is sort of a question of observational symmetry. If we do kind of the inverse SETI inquiry and ask, given our current state of techniques, Doppler transit photometry, transit spectroscopy, what's the footprint of our Earth out there, and when does that area overlap with what you're finding out there in terms of Earth-like?
So the Kepler spacecraft was designed to detect an Earth-Sun analog. So with 3.5 years of data, we should be able to begin to see them. As I said, we've analyzed about 1.5 years worth of data. So over the next year or 2 years, as we complete that analysis, we will have data in hand to see an Earth-Sun analog. Doppler method, again, that Doppler signal due to an Earth out at 365 days is going to be some centimeters per second. We do not currently have the technology to detect that. Does that mean that we will never have the technology? No. I'm hoping that, especially with this kind of result like Alpha Cen B, that we will invigorate investments in instruments that are capable of achieving sub-meter per second precision, but we're not there yet. Did you want to say something more?
Now, in terms of the observability of our system, it's along the ecliptic, for instance, just wondering, who out there can see us?
Oh, that's an excellent question.
That's the inverse question.
Yes, absolutely. So as I said, and you're pointing out, the Earth is casting its own shadow out into space. So presumably our shadow is sweeping across stars out there in our own galaxy. And there is somebody who's gone to the trouble of calculating, at least in the solar neighborhood, which stars those are. I don't have them off the top of my head, but they exist, right? So there could be somebody else out there who's doing the same exact thing and finding evidence of us. Absolutely.
My question is really of the future. What kinds of missions does NASA or the ESA have on the planning boards for future missions to improve the accuracy of the Kepler mission, or alternatively enhance the wobble method to detect planets?
There is nothing being developed at this moment in time except for the James Webb Space Telescope. The James Webb Space Telescope will be able to probe the atmospheres of some of the larger planets, Jupiters, maybe even Neptunes. They're hoping to be able to do maybe 1 or 2 super-Earth atmospheres through this kind of what we call transmission spectroscopy, catching the light that has filtered through the atmosphere. So JWST will do that for some of the larger. But there are 2 missions that are currently in the proposal stage. One is called TESS. TESS is a mission that is very much like Kepler, except that it's being designed to find planets near the solar system. So it wants to do more of a whole sky survey, focusing only on stars that are very close to us. Kepler is doing a statistical survey of the galaxy, probing a slice of the galaxy out to 3,000 light years for statistics, right? Whereas TESS would want to look at the whole entire sky to try and find those transiting planets that are closest to us. Because those would be really good candidates for JWST or some kind of a characterization mission that could look at atmospheres, right? So something like TESS is going to be the next logical step. Let's find those transiting planets that are closest to the Earth. Those are going to be the best candidates for doing observations that probe their atmospheres. So I'm hopeful that that will pan out.
That's TESS?
TESS. Mm-hmm. Yes?
If you were to use the wobble technique on a planetary system with many planets, how would you be able to pick out the different planets from the generalized result?
Such a good question. So every planet in a system is tugging on its star, and they're doing so at different times. So if you have one planet, it's really simple. It's like the cartoon I showed, right? It's just going to wobble back and forth. But if it's being tugged in lots of different directions, it's going to do something much more complicated. You have to look at that data, look at that complex pattern, and you have to be able to fit multiple signals in order to understand what's truly there. And that means that it's going to take more time. You need to take more observations to really see that long-term pattern to be able to disentangle all the different planets that are there.
Thank you.
You're welcome. Oh, yes.
First, I'd like to say excellent talk, of course. Thank you very much. You had mentioned a few times that there are astrophysical processes that can simulate what would look like a transit to us.
Yes.
Can you say anything about those? Are they just periodic dimming of the star?
Absolutely. Astrophysical signals in nature that mimic planet transits. Imagine you're observing a star. Of course, in your telescope, on our digital camera, we don't see it as a round star. We just see a smeared out blob of light, right? We don't have it, it's not resolved. We don't see the surface of the star. If behind the star, someplace distant in the galaxy, there's another star that happens to be aligned with your star, and if that other star itself is an eclipsing binary system, so 2 stars orbiting one another in a configuration that causes them to eclipse one another, what you're going to see is the sum total of all of those photons. This thing that's really far away and faint, that's dimming every once in a while, contributing a small percentage of light to this total. And that's going to end up looking like a tiny dimming of light. And so we have to be able to vet those out.
Great, thank you.
Uh-huh. Yes.
I'm wondering about the 4-star system that you were mentioning there.
Yeah.
That's a fairly complex system, and I'm wondering if what you're seeing is something that has enough of a chaotic component that it's not long-term stable, And what we may be seeing is something that's just, say, a passing pair, but we're seeing it sort of in a snapshot form where things are going on temporarily, but it's not actually long-term stable.
That's a great question. These circumbinary planets all have that peculiarity. And it's very complex, actually. I didn't get a chance to go into this, but I'm going to take the liberty of doing so now that you've asked the question.
Okay.
If you're looking for planet transits, you've got a dimming of light, and it occurs at some normal periodicity, and it's always the same. Now, if you have a planet that's transiting a binary system, all bets are off. It looks completely different, right?
Right.
Because first it transits one star that has one temperature and produces a certain amount of dimming, and then it transits a different star, and maybe that occults a lot more light because that particular star has more energy per unit area. Moreover, here's the thing. Let's think about how long the dimming of light lasts, okay? That's really easy if the star is stationary.
Right.
Every time it's going to be the same. It's just the time that it takes that planet to move from one side to the other. But what if the stars themselves are walking around? If the planet swings around and transits while the star itself is moving in the same direction, the transit's going to take a long, long time.
Right.
But then the star comes over here to the back, and now it's going opposite the direction of a planet, potentially. They're going in opposite directions, and that's going to make the transit duration very short. So it creates this light curve that's extremely complex. It makes the detection of these things completely different. We have to employ different techniques in order to be able to detect them. But here's the thing. Because of all these differences, you get a tremendous amount of information about the total system.
Right.
You can get the masses of the stars involved. You can see gravitational interactions, not just between the stars themselves, but between the stars and the planets, and between the planets themselves. And all of this complex dynamical information allows you to recover unique solutions about the characteristics of that system.
Right.
So it's very difficult to have any kind of astrophysical false positive mimic that complexity. The other thing that I was going to say is about the stability.
Yeah.
Once you know the properties of the system, then our theoreticians can plug in all the physics, all the gravity and physics, and just make a simulation and hit the button and say go, and see how long the system lasts. And they can run that millions of times.
Right.
And they calculate the time scale for dynamical stability. And in all of these cases, they're all dynamically stable, surprisingly enough.
Oh, even something like the four-star
Even
system.
like the four-star system, that's
Is
right.
the four-star system stable because the two pairs are far enough
That's right.
apart? Okay.
That's exactly right.
That
It
makes
all
sense.
boils down to the ratio of the separations.
right.
As long as they're like 4 times, the planet is something like 4 times further away, it's
That was exactly my thought, because you get them all, you get 4 of them together, you got a mess.
exactly.
Okay, thanks.
So we're just going to take a few who are now standing.
Okay, all right. So just the people who are now standing, I guess we'll go to this side.
Is Kepler getting enough data that they can start to analyze the size of planetary systems through their evolution over time, since you'll have stars of different ages that you're looking at?
We do have stars of different ages, absolutely. And so I suppose you could say that they are giving us information about the evolutionary state. What we're finding is that it's very complex, because the dynamics of these systems, the fact that you have Jupiter-sized planets at short orbital periods means that the systems, planets are moving around. So things, it looks like planets don't just form and then stay put. They form, they interact, they collide, they have friction, drag with a disk, they move around, they eject one another. It's very chaotic, especially in the early stages. So it's going to be very difficult to recover the history, to be able to see patterns that are evolutionary in nature. I think that's going to be very difficult. But we do have ages for some of our stars. In fact, we have a very detailed campaign to study the rotations of stars, because rotation is an indicator of age. If you can get the rotation, you can get the ages of the stars. And we can get the rotation because Rotation is going to leave an imprint in the brightness measurements as a function of time. So, yeah. Yes?
I'm just curious why it takes so long to reduce the data down. I mean, a year and a half, and we're 3+ years into the mission now. Could you explain the complexities involved in that and why it takes so long?
There are multiple answers to that question, multiple components to it. Every time you add more data, the computation time grows not linearly. It grows as some log or exponent, right? So we have computation time. However, to offset that, we have migrated a lot of our software to the supercomputers here at NASA Ames. So that's not, it's an issue, but it's not too much of an issue. More importantly are the improvements that we have made to the pipeline algorithms that are going to increase the completeness of the sample. We have stated in every single one of the papers that we have published that due to, I hate to use the word immaturity, but due to the status of the pipeline, the analysis pipeline, the sample of planets that we have presented to the public is not complete in that you would expect, I mean, we have a detection threshold. We say, okay, if the signal is so big, and we measure that in units of standard deviations, you know, which is the uncertainty. If it's 7 times bigger than the uncertainty, we call that a statistically significant detection. Is it true that we have detected every single statistically significant event in the data? And the answer is no, because we are suffering from pipeline incompleteness, because the pipeline, as scheduled, is maturing with time. So that's another issue. The third issue is that we are devising procedures that are creating a more uniform, statistically uniform sample from which the public and the astronomical community can derive statistics. So we are devoting a lot of time and energy into devising these procedures. So instead of racing the clock, trying to get out as many planet candidates as we can early, we are taking a more methodical approach to try and produce a comprehensive, high completeness, highly reliable sample of planet candidates from which you can derive robust statistics. So our next big catalog release is going to be using 12 quarters of data. So 12, each quarter being about 3 months. So almost a full 3 years. Whereas the last catalog that I showed you utilized six quarters of data. So the amount of data is going to double. On top of that, you're going to get higher reliability because our vetting metrics have improved, and you're going to get higher completeness so that people can go out and do the statistics. So that's the short answer. Yes.
You just mentioned that you may be able to tell something about the rotation of stars.
Yes.
Can you tell their axis, and can you, for multiple planet stars, can you tell what plane they're rotating in?
In some cases, yes. We can get the obliquity of the star system or the planet, right? One question is it true that planets are always more or less orbiting along a plane that is perpendicular to the rotation axis? And Doppler surveys have shown us no, that is not always the case. However, all of these multiple systems that you just saw are very highly coplanar. Those planets are all orbiting on the same orbital plane. And so you do expect those to be coincident or perpendicular to the rotation axis, but we know that there are going to be exceptions. And there are ways of figuring out what that angle is. And then to take that a step further, what is the angle of the spin axis on the sky relative to that orbit? So those are all different projected angles. And you can calculate those for very specific cases. I'll name 2. If you have a large radial velocity signal and the planet is transiting, the planet is going to transit first the side of the star that's rotating towards you, and as it moves over, it's then going to transit the side of the star that's moving away from you. That's a velocity difference. First it blocks out light that's moving towards you, then it blocks out light that's moving away from you. And so that introduces a systematic signal in the radial velocity data called the Rossiter-McLaughlin effect that gives you that obliquity. Okay, so that's one. But that requires radial velocity data. But here's another that requires only Kepler data. You can do this with Kepler data alone if the star is spotted, has spots, like our own sun has spots, and if the planet passes over the spots themselves. Don't laugh, we've done this. I'm serious, we've done this. It's in the literature. That gives you the obliquity measurements because it's a little bit different each time. So those are the two methods that I know of that are currently being employed in both yielding fruit. Yeah. Oh, last question, yeah.
The diagrams you show always show circular, at least low eccentricity orbits. Is that the case, or is that only because your technology only sees very circular orbits?
You're so smart. It's because we assumed circular orbits when we did our modeling. Yeah, we have no information about eccentricity. Sometimes we do. That's not exactly true. In some cases, we do have information about the eccentricity, but in general, for all of our catalogs, it has been the case that we assume eccentricity equal to 0 and then do the modeling to recover the planet properties. Now, here's the thing. Imagine you had a multiple star system. A multiple planet system. Multiple planets, all orbiting at a different distance, and you look at the duration of the transit, right? How long that dimming of light lasts, okay? So the duration of the transit depends on the velocity of the planet in its orbit, and the velocity of the planet just depends via Kepler's laws on the distance and the mass of the central star. So the geometry of all of the different planets in that system should yield consistent durations. Kepler's laws tell us that the more distant the planet is, the slower it moves in its orbit, and therefore the longer the duration of the transit is going to be. Okay? So you should see a pattern. If, however, you have eccentricity, that means the planet comes in at periastron and then slows down at apastron, peri-ap. That means it's going to speed up, slow down. You're going to have slightly different velocities. You should be able to see that in the durations of the transits themselves. They'll be slightly different. It won't follow that same logical pattern of Kepler's laws. So you can infer information about eccentricity in some specific cases, but generally speaking, you need Doppler measurements or transit timing variations or some other information to give you that parameter.
In general, do astronomers believe that most orbits are circular, like our solar system, or are we an exception?
Not necessarily. The Doppler data is not proving that to be the case, no. No, eccentricities are quite common. Yeah.
All right, I'm going to take the last question, which is, tell us when we can look forward to the next catalog.
To the next catalog?
Next catalog release.
Oh, God, I'm going to get myself into trouble in predicting. I'm always breaking promises, so you have to take it with a grain of salt. But we're shooting for something like mid-next year. Now, we're going to have an intermediate small catalog release based on a smaller set of data, probably somewhere around the beginning of 2013, maybe the end of 2012. Significantly smaller, maybe on the order of some hundreds of new planet candidates, but on a significantly smaller data set, so you shouldn't expect any of the most interesting planet candidates. That will come with this other big analysis that I spoke of, which we're shooting for finishing mid-next year, and now that I've said it, I'll be sure to be wrong. So.
Well, let's thank Dr. Bhatia for a wonderful talk.
Thank you. Thank you for coming.